All right, we'll go ahead and get started while she's getting set up, but welcome to, I think we're PS45, Haptics Touch and Feel. And I believe this is also the last session of the day, so hopefully you chose wisely. But Yujie is going to be the first speaker, and as soon as she gets it up in presenter mode, I'll hand it over to her.
Whoa, okay. Hi everyone, I hope everyone can see me. I'm Yujie and I'm a PhD student at Stanford. And today I'm really excited to share about this work that looks at the impact of shared body sensations on social interactions in virtual reality. And this work is done in collaboration with Jordan Egelman, advised by Professor Jeremy Bailenson. Thank you. Body sensation, like the sense of touch, are essential to how we experience and interact with the world. It could be you feeling the texture of an object or noticing the sensations from within your body. So normally body sensations are private because only the person experiencing the touch truly knows how they feel. But to build social connections, often people seek to understand and share what others are feeling. Sayings like, "I feel you," reflect the tendency of people to relate to others' experiences by metaphorically feeling what other people feel in their bodies, including associating both emotional and physical understanding. The same type of aspiration reflects in other cultures as well, and here I'm showing a common phrase in Chinese, which translates as establishing social connections by being not only emotionally aligned, but also bodily felt. So what happens when one can physically feel what others are experiencing on their body? This is the key question driving this project. It turns out that psychologists have been long interested in this inquiry and study it in psychophysics experiments. By synchronously brushing the participants' face as they watch another stranger's face being brushed the same way through a video, the participant reported an illusion of looking at another person's face, but having the feeling of looking at themselves in the mirror. Those type of synchronous brushing have been found to increase empathy, as well as facilitate emotional recognition. While past work uncovered the benefits of shared body sensations through highly controlled psychophysics method, the practical impact of this technique on social interactions are rather unknown. Feeling brushing sensation on the face while observing another person being brushed the same way diverge from day-to-day experiences. So in this work, our goal is to understand the impact of shared body sensations in naturalistic social settings. And in particular, we focus on social interactions in virtual reality. Virtual reality as an emerging type of social media transforms how our social interaction looks like. People can do interaction that transcend what is physically possible, such as embodying avatars that are drastically different from their own identity. With the emergence of haptic technologies, we see a growing awareness of incorporating touch feedback into social interactions in VR. Although shared body sensations are not typical in our physical interactions, they fit well in VR in transforming our social interactions on a bodily level. And we see many applications in VR, such as those asynchronous concert or VR support group, users often passively observe interactions without being socially or physically co-present with each other's. And shared body sensations could potentially offer an actual layer of connections. So with this goal to understand the impact of shared body sensations in social interactions in VR, we conducted a user study with 32 participants. In the study, participants were positioned in front of a dyad of virtual agents. They were asked to watch a conversation in between the two virtual agents, which were pre-recorded, and then this is similar to asynchronous communication that we commonly see in VR, where the users are revisiting past conversations. And the study adopted a within-group study design with two primary independent variables. In this talk, I'm going to focus on our first independent variable, which is whether participants feel shared touch or no shared touch with each of the virtual agents. And in particular, in the conversation that the participant observing, they shared touch with one of the virtual agents they observed. So for demonstration purpose of this conversation, I've highlighted the virtual agents on the right wearing the white shirts as the agent participant will share touch with this following presentation. So what this means is that whenever the white shirt agents receive touch on their body, participants also receive haptic feedback on the corresponding body part. We leverage two types of haptic devices to render the touch feedback on the participants. One is a pair of haptic armband, and the other is the controller held in hand by the participants, and both render vibro-tactile feedback. There are three types of touch events pre-programmed in the conversation that participants observed. The first one is being touched on the forearm. So in this case, when the white shirt agent was touched by the other agent on the forearm, the participants also feel vibro-tactile feedback on one of their forearms. And the second touch event is touching others with hands. So in this case, when the white shirt agent was using her hands to touch another virtual agent, participant felt vibro-tactile feedback through one of their controllers. And the last touch event is pressing hands together. So here, when the white shirt agents are pressing her hand together, the participant felt vibro-tactile feedback through both of their controllers. And when facing another person, we often see left-right confusion because of reverse perspective. This is the difficulty to tell left or right from the perspective of others. So to ensure the generalizability of the results, we thus incorporate a nested factor in this independent variable, which is the side of body the shared touch was mapped to. Basically, half of the participants will feel the shared touch on the same body side as the virtual agents they share touch with. So in this case, when the white shirt agents feel touch on their right forearm, participants also feel it on their own right forearm. And the other half of the participant actually received the shared body sensations on the opposite side of the body, which means here when the white shirt agents receive touch on their right forearm, the participant actually feel it on the left forearm. We employ a wide range of measures. After each conversation, we ask participants to rate body illusion, empathy, social attraction, and attention toward each of the virtual agents. As we are a forced spatial interaction, we also incorporate behavioral measures. This involves asking the participant to physically walk toward the virtual agent they just observed as if they were going to join the conversation. With this behavioral task, we're able to collect data such as interpersonal distance and their final standing locations. So putting everything together, here's the overall procedure for the study. Participants started off getting themselves familiarized with the haptic device and initial introduction about the concept of shared body sensations. Then participants got familiar with their own virtual body. Then participants watched a 5-minute conversation between two virtual agents. And after the conversation, participants were asked to join the diet of virtual agents as if they were going to join the conversations. And here I also summarized the self-report measures we collected before and after each conversation sessions. The whole process were repeated 2 times to accommodate 2 different types of conversation topics. And here I'm going to show some of the findings through our studies. Overall, participants reported a stronger body illusion toward the agent they shared touch with compared to the one without shared touch. The trend preserves regardless the shared touch was mapped to the same or opposite side of body, which is the nested factor we included in this independent variable. However, we do notice that when the shared touch was mapped to the same body side, the participant reported even stronger body illusion toward the virtual agents. In the submeasure of body illusion, we see a very similar trend. It shows that participants develop a stronger body ownership toward the virtual agents they previously shared touch with compared to the one without shared touch. They also develop a stronger attachment to their experience, to their appearances, as well as response to the multisensory stimuli they felt. They see others get felt. We use the inclusion of other in self scale to measure the empathy level that participants felt toward each of the virtual agents. Participants were presented with visualization shown on these slides, and then circle out which of those visualization best describe their relationship with each of the virtual agents. And we see that participants reported a tighter relationship with others when there was a shared touch, and this indicated a stronger level of empathy. We also measured social attention and attraction. Participants fell over each of the virtual agents. However, there was no statistical significance that we observed in either of the measure. And behaviorally, at the end of the conversation, we asked participants to physically walk to the dyad of virtual agents as if they're going to join the conversation. And we found that in 40 out of 64 trials, participants chose to stand near the virtual agents they previously shared touch with. And here we show the visualizations of the actual walking path for each of the participants. The orange lines indicated that they were walking toward the virtual agent that they previously had the shared body sensations with. We also analyzed the minimum interpersonal distance between the participants and each of the virtual agents as well, which is measured by the distance between head positions. We found that participants tend to stay closer to the virtual agents they previously shared touch with, as opposed to one without any physical connection. So to sum it up, with shared body sensations, we see participants reported stronger body illusion and empathy. And behavioral, they tend to choose to stand closer to the virtual agent they previously shared touch with, as opposed to the one without shared touch. We see the finding of this work to unlock new interactive possibilities in social VR. By sharing body sensations with other users in VR, users can develop a deeper social connectedness, even though they are not physically co-present. And outside of VR, we truly believe in this work could help inform the design of haptic technology that aims to physically connect individuals. Just at ISMAR this year, we saw this amazing poster on specifically looking at how we can mapping touch of one person's touch from one person's finger pad to another person's wrist, and then to support social connectedness in remote conferencing setting. And this is a very amazing poster everyone should also read on top of this one. And lastly, I want to end this talk with some future directions, and I'll discuss it through both the design side as well as psychological impact side. So when designing for shared body sensation experience, we suggest future researchers to be considerate about leveraging training as part of the experience, as well as giving user full control of the amount of shared body sensations they can feel. Moreover, individual sensitivity to sensory feedback need to be taken into account to mitigate sensory overstimulation. More exploration are also needed to actually looking more into the investigating the psychological impact of shared body sensations. We see future work can extend the explorations to more live and spontaneous interaction context than pre-recorded conversations or more asynchronous type of interaction explored in this study. More haptic technique beyond vibro-tactile feedback can also be leveraged. And last but not least, we see tremendous opportunity to actually study the long-term impact of shared body sensations. And with that, I'll end my talk here. I'm happy to take any questions.
We've got a couple of minutes for a couple of questions.
Very interesting talk. Thank you very much. Do you think the appearance of those avatars affect the result? Like, not the female avatars, but the scary monster or something like that. Maybe the touch might have a negative effect?
Yeah, for sure. We definitely consider the appearance of like the avatars you're observing as part of the potential confounds in the study. So specifically for this study alone, we do customize the avatars you're observing based on like what demographics you are. So like participants are always paired with avatars that's of the same gender and demographic experience as them. But we didn't really study when you're like observing avatar that's like non-humanoid, but I think it's a really good like future work to look at how appearance and how different it from you may potentially impact on the effect of shared body sensations.
Thank you.
Yeah. Hi, I'm Jan Negar from Inriaren. Thank you for your presentation. It's really great, really interesting work. I was wondering about the haptic feedback. since it was vibrations, I know that sometimes it can be felt as aggressive by a lot of people. Do you think a different type of haptic feedback would have worked similarly? Do you have any like future works planned for that, or yeah?
Yeah, for sure. So for this particular study, we chose vibrotactile feedback mostly because it's the most widely adopted type of haptic actuation we have, and we're really interested in seeing, oh, even when the touch feedback is not exactly like how human touch feels like, does this still work? And it turns out from our study results, even with the simplest vibrotactile feedback, people can still make that social association with the person they have that physical connections with. And I do agree with like more realistic actuation methods that simulate more like human touch, we might see a stronger effect. But I agree it's a very promising future directions on looking at different actuation methods.
And
Did you, sorry, did you ask them like what they felt about the feedback? Like, did some people hate it and that's why it didn't work, or?
Yeah, so in your supplemental material, we actually recorded some of the qualitative feedback from the participants. I think the most part that some people, like a few people don't like it is because sometimes it distracts them from the conversation they're observing when considering you have both the touch feedback as well as like the voice you're listening to. But none of the feedback were actually about if like the vibration was too strong or anything. Yeah.
all right, let's get set up for our next speaker. All right, and take it away, Kenichi.
Okay. So hello, I'm Kenichi from DiverX, based in Japan. I present about our research about close vibration device to evoke the perception of strong wind. This project was conducted while I was at the University of Tokyo as a PhD candidate. I thank my co-authors Juro, Kei, Yuki, and Shinichi for enabling this work. So this is a quick summary of the proposed method. Our device enables to provide strong wind perception without actual strong wind. It is achieved by a wearable haptic device to vibrate clothing. I will explain some backgrounds. Researchers have been working on a kind of haptic device called wind displays. The wind displays can simulate wind sensation to the users to enhance immersion, self-motion perception, or enhancing emotional responses. So some VR applications utilize strong wind stimuli for various purposes, such as disaster education, simulating tornado experience, or replicating air resistance or teleportation. However, blowing intense wind to the whole body needs a very large fan. So such a large device takes up space and energy consuming. So our question is, can we create haptic experience of strong wind without actual strong wind? So our idea is to reproduce haptic stimuli which we experience in actual strong wind. So like this video, when we are in a strong wind, we experience a phenomenon that our clothes fluttering. So therefore, we made a haptic device to reproduce such a fluttering motion of our clothes. Clothes vibration can be reproduced by a lightweight and smaller device compared to the actual strong wind. So there is some previous work about using multisensory stimuli to change the perceptions of wind. When we receive multisensory stimuli, a cross-modal effect, which is an interaction between multimodal perception occurs. So one example is Nishimaki and colleagues' work, which found that visual scenes representing different wind velocities alters perceived wind velocity. However, because the perceived wind tended to be weakened by their method, so it couldn't be applied to create strong wind perception. Other researchers proposed to move the user's clothing with string to express various haptic sensations, including wind. Although this is similar with our idea, but they did not experimentally verify whether the vibrating clothes induce a cross-modal effect and enhance the perceived wind velocity. In the rest of my talk, first I report a result of measurement of fluttering clothes in the real strong wind. Second, we developed a wearable device that reproduces such motion of clothes. Finally, I explain about two user studies that verified the changes in perception with our device. To simulate realistic sensation caused by a strong wind, we measured the motion of clothes in the wind. We measured the clothes using a hairdryer and laser displacement meter, and found a large peak was observed at 13 Hz at a wind velocity of 15 meters per second. Therefore, we created a device to reproduce a vibration of about 13 Hz. The device can be attached to user's arm like a sleeve and comprises a cross and actuator unit. We selected a motor and a link mechanism to make a low frequency and large deformation of cross. So this mechanism produces a linear motion and moves the cross back and forth. We conducted an experiment to evaluate possible changes in the perceived wind velocity and the cross vibration. We presented actual wind and cross vibration simultaneously and evaluated whether the perceived wind velocity changed or not. To blow wind, a hairdryer was placed to the right of the participant's right arm, and the right arm wearing cross vibration device. By combining the presence or absence of cross vibration and 3 actual wind speeds, no wind, 7 meters per second, and 11 meters per second. So we prepared 6 experimental conditions in total. For each condition, participants experienced wind stimuli twice, reference wind and comparison wind. The reference wind was blown at 7 meters per second, and the cross vibration device was not operated. After 5 seconds interval, the comparison wind was blown according to the experimental condition. And the participants were required to compare the reference wind and comparison wind and answer the questionnaire about perceived wind velocity and realness of wind sensation. So this is the result about the perceived wind velocity. As you can see, stronger wind was perceived with cross vibration in the conditions of no wind and wind of 7 meters per second. This result indicated that the perceived wind velocity is enhanced when the actual wind was absent or not very strong. So this is the result of evaluations of realness of wind sensation. We obtained an interesting result that the tendency is contrary between conditions with actual wind and ones with no wind. When there was actual wind, the realness decreased with cross vibration. So might be because the vibration felt artificial and less real. When there was no wind, the realness increased with cross vibration, despite there was actually no wind. This can be explained as a pseudo-wind sensation, uh, which tactile stimuli like vibration cause a pseudo-perception of wind. We conducted a second experiment with adding visual stimuli, because the visual stimuli also can alter the perceived wind velocity according to the previous work. So we used mostly same apparatus as experiment 1 and displayed a virtual scene of avatars' clothes swaying in wind on an HMD. We combined the presence or absence of cross vibration and 3 levels of visual movement: static, weak fluttering, and strong fluttering. So we have also 6 conditions in total. I skipped the description of the procedure because it is almost same with experiment 1. But we modified questionnaires to be answered within virtual environment and added questions about the sense of presence. So this is the results about the perceived wind velocity. Same as in experiment 1, the perceived wind velocity increased when the cross vibration is on. So this suggests that the strong wind perception also can be evoked during VR experiences. On the other hand, the main effect of visual stimuli was not significant. To discuss the perceived wind velocity deeper, I am showing the summary table of the results from previous research from Nishimaki's team and our results. Both research indicated that the visual stimuli is less effective when the actual wind is strong. This may be because if the skin stimuli from the wind is strong or strong and very explicit, the cross-modal effect becomes rather weak. On the other hand, cross vibration evoked the changes in the perceived wind velocity, even in the condition of 7 meters per second wind. So haptic stimuli from the cross vibration can alter wind perception in a broader range of wind velocity. I am also showing the highlights from the results about the sense of presence. We found significant differences for spatial presence and realness. For spatial presence, cross vibrations and visual scene of fluttering cross both significantly enhance the spatial presence score. For realness, only visual scene enhanced the score. So although the visual stimulation has no significant effect on the perceived wind velocity, it improves the spatial presence and realness of the experience. We consider that this is because the visual scene of fluttering clouds can enhance the consistency between the wind and visual stimuli. So this slide concludes my presentation. We developed a wearable haptic device to make the clothes flutter as if it is in a strong wind and enhance the perceived wind velocity. Our future work includes applying this method to other body parts to achieve a full body experience of the strong wind. And it is also an important challenge to maintain the realness of wind during the cross vibration. Yeah, this is this concludes my presentation. Thank you for listening.
And we have time for one quick question while Tom comes up and sets up the presentation, the next presentation. Oh, you have a question? Here, you can use my microphone to answer.
Thank you for your presentation. It was a very fun experiment. Do you think this kind of thing could work for the whole body or mostly for only for sleeves? Because sleeves are a lot easier to move around. Could you make this portable, for example?
Your question is about creating full body experience or strong wind, maintaining mobility. That's important perspective. So if we use a bulky device such as air pressure system or a string connected to fixed frame, it may be lack the mobility. So using motor and link mechanism can make a lightweight mechanism to make cross flutter. So by this method, we may able to make a full body experience of strong wind without very large equipment.
Thank you so much. Our third speaker is Tom, and I'm going to hand it over to him now.
Hello. So my presentation on ThermicVib enabling dynamic thermal sensation with multimodal haptic glove for thermal responsive interaction. My name is Hyung Lee, also Tom, and my team includes Hojeong Lee and my advisor Sang Yoon, and we are from KAIS. And I'll begin my presentation. So for first introduction, to render the thermal sensation on the hand, there many has been studies for the thermal haptic devices. Most of the ways used in pneumatic ways, which uses liquid pressures or air pressures, and for mid-air, which aims to not use any actuators on the hand. And there's, for the easy way and most popular ways, the thermoelectric devices basically just uses electric current to render both cold and hot sensation. While pneumatic and mid-air has a advantage of delivering stable thermal sensation, they require external hardwares. And also for the TED, although it is easy to use, it has to cover more areas, you have to consider more actuators, which causes hardware burden for the users. So to solve this problem, many people, recent studies uses thermal and tactile sensory illusions, which basically able to cover large areas using less actuators. So for tactile actuators, they use phantom sensation to cover more areas than actual tactile feedback can do. And for thermal referral, they uses the tactile feedback and thermal feedback to cover larger areas of thermal feedback. So simply explaining the thermal referral. Thermal referral is a phenomenon that when you use tactile stimuli and thermal stimuli together, the thermal sensation actually localizes into tactile stimuli nearby. So by using this, recent studies were able to cover other areas without using thermal actuators on that spot. And for the phantom sensation, they uses 2 or more tactile stimuli to create a new phantom tactile stimuli between the actuators. So they were able to create using static vibration to create a static or dynamic tactile sensation. So our motivation was that because thermal referral uses tactile stimuli and thermal stimuli, and phantom sensation is also considered to be another stimuli, tactile stimuli, then when we combine them, the thermal sensation also could have a static and dynamic characteristics of a phantom sensation. So our contribution is that we created dynamic thermal sensation on the whole hand with wearable haptic interface, and we integrated the thermal referral and vibro-tactile phantom sensation. And using that integration, we proposed a novel thermal haptic rendering pipeline. So for our methods, this is an overview of our process. And first of all, when in the VR scene, we conducted this all in the VR scene. And in the VR scene, when we get the hand position, the system leads to and trying to find if it is in the contact condition or non-contact condition. And based on that, the computation goes differ and heat changes are computed accordingly. And we go to the rendering process where each parameters for actuation of tactile and thermal actuators are calculated and sent to the actual MCU with a UDP communication. And according parameters sent is what makes the arrays and peltiers work accordingly. And as a result of that, the users feel thermal sensation for that. So we go to the detail. For the pre-process, our research question was how to provide the feedback for the user interactions. So in the VR scene, we can use the whole hand, but we also use part of the hand to interact with the thermal objects. So we wanted to provide feedback partially and wholly together. So for the sensation localization, we defined 24 interaction nodes for the coordinates for the thermal sensation. And we also defined the thermal coverage of FTEDs, also known as thermal actuators, to easily compute the thermal rendering. And we also defined the node groups, which are 5 fingers and 3 areas on the palm for easy computing tactile rendering. So to localize the thermal interaction and trying to find where to render, we use the heat changes upon the user's action in the VR scene. So to find the temperature difference based on the user's action, we use the heat capacity equation to find the temperature difference in unit time. So and also we also wanted to consider the interaction. So we did 2 equations which consider contact and non-contact situations. So for the contact situations, this one happens is when you touch a thermal object with your hand. So when that happens, the interaction nodes that is included in the interaction and affected by it will have a heat conduction for their heat changes. So then as a result, the result becomes the heat conduction, how much they have touched the object and how much heat has transferred from the thermal object to the finger. And for the non-contact, it is based on the view angles and the distance from the thermal object to the hand. So each interaction nodes are calculated based on that, and the heat transfer happens with the result of a heat change. So after the computation, the heat changes goes to the rendering process. And the research question on this process was how to translate those heat changes to actual activation of the tactile actuators and thermal actuators. So for the thermal rendering, the highest heat change value from each thermal coverage, as mentioned, are considered as a target temperature for the PIDs. So for the PID control, we have a target temperature, and we trying to reach and stabilize the target temperature until the interactions are finished or interaction is changed. So these are the actual control of the FTEDs, and we have 3 modes: 0.5 degrees Celsius per second, 1.5 and 2.5 for the outcome to be actually expected by the users, because we don't want to be speed changing continuously to interrupt the user's interaction. So for the tactile rendering, we consider 2 contexts. First one is each group. So each group actually have two tactile actuators. So we decided the relationship between the 2 of them with a group weight. And after that, whole hand weight is applied to the intensity to consider which group has the highest heat change. So, and the final intensity reflects both contexts for more detailed interaction when the users are interacting with the thermal object. So for the methods, we wanted to know how to set up the actuators to achieve the intended feedback. So These are the actual hardware, and we placed the two arrays on each finger and each palm. And we placed the thermal actuators only on the thumb, index, pinky, and palm. We didn't place the middle finger and the pinky finger because you can actually feel the thermal sensation on the middle finger and the pinky finger with only thermal referral. So by using the vibral tactile feedback, you can send the thermal sensation there with thermal sensation. So for the user studies, we conducted with 21 participants with 13 male and 8 female. So for the first study, we did a point localization and pattern recognition for the accuracy of our thermal sensation. So for the static point localization, we only there are 24 points for the users to feel and choose which one is the position is. And for the dynamic, we show the 20 thermal patterns for the users to identify and answer them. So these are the 24 locations we defined. And for the point accuracy, for each point, the average was quite low, 61%. And so we had to like combine the most confused one within the groups. And B shows the redefined one, which shows the 85% of accuracy. And for C is a thermal group, which is basically 5 fingers and 3 palm areas, which all show the high accuracy. And you can see the middle finger and pinky finger also was easy to identify the thermal sensation without the thermal actuators there. And for the 20 patterns, we were able to get the 80% of the accuracy. However, there were 3 patterns that were quite low, which was 52%, mostly because there was a space on the glove and the hand. So it was kind of confusing for the users to decide. For study 2, we actually conducted interaction in the VR scene. So 2 scenes were shown, one is a contact is where you interact with a cat with a different temperature defined. So when user touches the cat, they were able to feel the temperature differences. And for the non-contact scene, users were asked to hold their hands out to the fire and asked to change the distance and the view angles of their palm to feel the temperature difference. These are the results from there. And in this scene, we also added 2 conditions. One was thermal only, so the vibration was not included, but still works with our algorithm. And multimodal is where vibration is added. And statistically, it didn't show the significant difference. However, in the detailed metrics, multimodal showed a little bit higher, slightly better. So we went deeper in why without the vibration was similar to the with vibration. It was that in the preference, users weren't expecting a high vibration when they're touching a cat or a fire. So in actual interaction, because the cat has a soft fur and skin, the vibration itself kind of dropped the immersion. So, but however, in the metric and the graphs, you can see that cats' multimodal preference rose compared to the thermal only because they do expect to have a tactile feedback on the cat when they touch them. So this gave our insight that when we rendering the thermal sensation, we need to match the target's characteristics. Otherwise, the user's experience can get lower. So for our future work, we want to add the cold sensation because when we say about thermal sensation, we often do include cold and hot together. So we want to find we will find the appropriate heat sink for our current form factor. And for the performance of actuators, I think we believe that if we apply better actuators, we will be able to achieve better rendering and better resolution. So we are currently doing the research. And for the insight from the preference questionnaire, we want to add more interaction consideration and trying to add different parameters for the interaction based on the object's characteristics and context. So in summary, we are able to combine the thermal referral and phantom sensation on the whole hand to explore the potential of introducing thermal movement experience with multimodal haptic interface. And also, we believe our approach enabled new thermal sensation and experiences to the thermal interface and thermal object interaction. Thank you.
We have time for one question while our next speaker sets up.
Just for the curiosity, how did you make sure it's safe?
I didn't mention in the hardware, there is a NTC thermistor, which is a temperature measurement for the Peltier. So we placed it on every actuators, and if we set the max temperature to 45, so if it goes over 45, the system automatically shuts down the Peltier until the Peltier is cooled down.
Okay, thank you.
All right, and our final speaker for the day is Steeven, so take it away.
Okay, thanks for the introduction, and also thanks to the previous speaker for setting the stage for thermal haptics. And just before I start, this work is in collaboration with Kenji, Ishihara, Moritz, Ziarko, Sebastian, and Florian from TU Darmstadt. And I would like to highlight how important is temperature actually in daily life. Like, for everything we do, we are basically collecting thermal data. For example, for the coffee in the morning, or also when you're opening your car's door in winter, you expect already something to be cold. So we are addressing basically the same problem as the previous talk, but from a slightly different perspective. And this is many of the haptic devices that you have out there currently require the user to wear something or to constantly grab something. And we do believe that the future of haptics is actually hand-free and doesn't require you to wear anything. So that's why instead of using these type of approaches of wearing something, we decided to go to encounter type haptic displays that for the ones that are not familiar with this technique is basically using real world objects with real world object properties to synchronize with the virtual objects in virtual reality. So for example, in here, you have that the person is touching this virtual object, and there is a robot actually locating an object over there. And this is dynamic for all the objects in the scene. And we have done quite some work in this area. First, we developed a plugin in order to facilitate the development of this type of haptics. Then we explore combining this also with ultrasound haptics, so we don't have only kinesthetic feedback, but also tactile feedback. Then we examine how this actually contributes to object perception, object properties perception. And the work that I'm going to present today is a contribution to this line of research. That is not only bringing kinesthetic, not only bringing tactile feedback, but also temperature feedback. So now let's talk about the thermal encounter type haptic displays. This is the prototype we developed. This is basically an end effector, something that you attach to the end of the robot, to the part that interacts with the user hands. And as you see, it has some coolers behind. I will go more in detail to this. It's a quite simple concept. We have a copper plate here, and underneath this, there are 4 Peltier modules that are heating up or cooling down the general plate. There are 4 sensors that are measuring the temperature in that location for every Peltier. And in the back, we have the coolers and the fans that are just counterbalancing the temperature, because for example, when you cool down this plate, the backside will get super hot. This is how Peltiers work, so we added this. For the control of the end effector, we did a very basic circuit. This is relay-based control. This is just turning on or turning off depending of the temperature we need. And as thermal phenomenon is very slow, as you saw in the previous presentation, this is not a problem because the temperature can hold for some seconds. And then we can easily control this. And there are also the sensor configurations. And this is how it looks mounted in the robot. It's around 1 kilogram, that is well below the payload of the robot, that is a Kinova robot. But now, okay, let's talk about the technical assessment about this. We did some relocation analysis, how fast is the robot, but this will be better if you check in the paper. Now, for the interesting part, that is actually the temperature. We saw that it takes around 1 minute to 2 minutes in order to reach a stable temperature. This is nice, but if we have multiple objects that have different temperatures in the virtual scene, is not the best practice, because then if we switch from one temperature to the other, will be extremely slow for having a realistic experience. So this is basically a thermal camera visualization of how the end effector change temperature. But yeah, this is just slow and probably not suitable for a realistic virtual environment. So besides this rendering technique, that is like the naive one of just heating up or cooling down the whole plate, we also develop a gradient style rendering technique that is basically having all the temperatures in the range. And now the problem is not about how fast the system can change temperature, but which spatial location we use for the user to touch. And we solve this by integrating the reach plus technique, that is basically redirecting the user hand to the goal temperature we want. So we move from a technical problem of having to make the Peltier faster to just an spatial problem, and then this simplifies a lot the rendering. So having this, we run a user study to analyze the overall experience actually of this technique. And we conducted a study with 24 participants, a very simple task, just exploring a virtual environment, touching different objects in the virtual environment, using the two conditions. One, using the thermal encounter type haptic display, and the other one just using the typical one, that is without temperature. And we, of course, use the gradient method, that is the one that we think performs better. We measure two things: sense of presence, that is measuring the overall virtual reality experience, and the haptic experience model, that is giving us more details into the specific haptic performance. This is how the virtual environment looked like. There were multiple objects over there, a toaster, an oven with different temperatures. And this is how it looked in real life. Like the object was, the end effector was relocating based on the object that is going to be touched. This is just for the sake of comparison how it will look synchronized real life virtual reality. So for the results, there is something that you might want to consider. This is not comparing haptics versus not haptics, but this is already comparing the benefits that encounter type haptic has versus the same plus temperature. So there is some feedback that is actually making the virtual experience a bit better. And we found it effectively, the realism is higher for the thermal encounter type haptic display. And this is interesting to analyze, because when it comes to the haptic experience model, the experience was, as you can see, a bit better, but not significantly better. This is because this one is evaluating more the plausibility of the feedback rather than the general experience, and both were already plausible. For the harmony, we didn't find any difference, because this is evaluating more how the haptic feedback is disrupting the experience, so it's fine. But for involvement, we found like, yeah, there is a significant difference. And then this analyzed the engagement based on the feedback that the participant might have. And the part where we found actually a lot of differences in the expressivity, that is how the different objects change depending on the phenomena that is happening in the virtual environment. So we also had some own questions, but of course it makes sense that the participants evaluated that it was easier to identify the objects through physical interaction because besides having kinesthetic feedback, they also had temperature feedback. And yeah, with this, I have three things that I would like you to take into account when reading this paper. One is that integrating thermal feedback in encounter type haptic displays improves immersion and the realism of the haptic experience. The second is that, yes, as we know that the encounter type haptics already improves the experience, but adding thermal is boosting up this part. And finally, even if thermal phenomena is slow in nature, just switching the rendering strategy will help already to have a faster way to render. So with this, I think I close ISMAR, but I would like to have your questions right now.
Hi, thank you for your presentation. I was wondering, oh, great presentation, by the way. I am very curious. I was wondering, did you try, because since we don't have great thermoception, especially, do you think with like a smaller plate and using diagonally coherent thermal feedback, so like warm, warm, cold, cold, you could do something more dynamic without having to move the plate? I don't know if I'm clear, sorry.
So having, instead of half plate, different quadrants with this, I think it is possible, but that will be more complex from the side of redirecting the hand, because then you will have to redirect to more specific areas of
Oh, no. What I meant is there have been some studies on it, is that if you want to have more efficient Peltier cells, so like faster heating up or cooling down, instead of having them just on and off, you can have like all of them on, but like at medium temperatures. And then the hot ones get turned off and the cold ones get boosted if you want cold, and versus. And so you could do that with a smaller plate and just achieve the temperature you want. And so, yeah.
Like presetting a neutral temperature and then switching. Yeah, but in any case, having that will still be slow because the copper plate has like a big area that is not only the Peltier, but it has to distribute across the plate. So it will be somehow slow. And if we have this space, I think with the other strategy might be still faster. Maybe with a bit more of power, you can make it faster, but it's not economical in a sense that you will just waste more energy in that sense. Yeah.
All right, one final question.
Yeah, like every time I see Peltier, it always have the same issue, the response time. Is there any like different approach for like thermal display that it might be faster? I know like there's like a infrared lights and then shutter combination for like a fast switching, but it only works for worms.
Exactly.
Yeah.
That one works for worm, and another strategy that is commonly used is using liquids, using fluids, but then it requires a pump, it requires like a whole system that is just pumping the material that is delivering the temperature. So Peltier, even if slow, seems to be like the way to go right now. Yeah.
All right, well, thank you so much for your talk and for all of our speakers. Let's give them one more round of applause. And that's all that we have. Just one quick reminder, from 5:30 to 6:30 is the closing ceremony. So just a reminder to attend that if you can. And thanks for coming and asking great questions and engaging with the speakers. You'll have a great day.